Have you ever stopped and thought about this? A machine weighing over 65,000 pounds, carrying 22,000 pounds of bombs, flying through pitch-black darkness over one of the most heavily defended airspaces in history for 10 hours straight. Not once, not occasionally, every single night for 3 years. That machine was the Avro Lancaster, and today we are going to break down exactly how it actually worked, because after this video, you will never look at a WW2 bomber the same way again. To understand the scale, think about what 65,000 pounds actually means. That is roughly the weight of 4 fully grown African elephants sitting inside a metal tube, being lifted off a grass runway at night with no runway lights, no GPS, no modern navigation system by a crew of 7 men, most of whom were under 25 years old, and that was just the empty aircraft. Add a full bomb load of 22,000 pounds, fuel tanks carrying roughly 2,900 gallons of aviation gasoline, and 7 crew members with their equipment, and you are now asking a grass runway in rural England to launch something closer to the weight of 5 elephants into the night sky. The Lancaster did this 156,000 times during the war. So how did it actually get off the ground? The answer starts with 4 engines that were, at the time, considered the finest piston engines ever built. The Rolls-Royce Merlin was a 1,649 cubic inch V12 petrol engine, 12 cylinders arranged in a V configuration, water-cooled, supercharged, each one producing 1,280 horsepower at takeoff. To put that in perspective, a modern family car produces somewhere between 100 and 200 horsepower. The Lancaster had 4 engines, each one producing 6 times the power of your car. Combined, the 4 Merlins generated over 5,000 horsepower before the aircraft had moved a single foot down the runway. But raw power alone does not explain how a 65,000-pound machine becomes airborne. Power gets you moving. Something else gets you flying. That something is the wing. The Lancaster's wing had a span of 102 feet, tip to tip. That is wider than the Wright brothers' entire first flight, but the size is not what matters. The shape is what matters. Look at any aircraft wing from the side. The top surface is curved, the bottom surface is flatter. This specific shape is called an airfoil, and it is the reason flight is possible. As the Lancaster accelerated down the runway, air began flowing over and under both surfaces of that wing simultaneously. The curved top surface forced air to travel a longer path than the flat bottom surface. Air traveling a longer path accelerates to keep up. Faster moving air creates lower pressure. Lower pressure above the wing and higher pressure below it creates an upward force. That upward force is lift. But here is what most people miss. Pressure difference is only half the story. The Lancaster's wing was also angled slightly upward relative to the airflow, what engineers call the angle of attack. This angle caused the wing to deflect air downward as it passed over the surface. And according to Newton's third law, if the wing pushes air downward, the air pushes the wing upward with exactly equal force. Bernoulli and Newton were not competing, they were cooperating. Together, they gave the Lancaster the lift it needed to get 65,000 pounds off the ground. The moment the Lancaster's lift exceeded its weight, something remarkable happened. Nothing dramatic. No sudden jump. No dramatic lurch into the sky. The aircraft simply stopped needing the ground. At a specific speed, determined by the wing's size, shape, and angle, the upward force became greater than the downward pull of gravity. The wheels lifted. The runway fell away beneath. The Lancaster was flying. That speed was approximately 105 miles per hour at maximum weight. The 4 Merlin engines reached that speed within about 2,000 feet of runway, on a grass field, in the dark, with blackout conditions meaning no lights visible anywhere for miles. The pilots who did this every night were not flying with computers or autopilot assistants. They were reading analog instruments by cockpit light and trusting the physics of a wing they could not see. Now here is where it gets genuinely extraordinary. A fully loaded Lancaster could carry 14,000 pounds of bombs to a range of 1,660 miles at 200 miles per hour. That range meant flying from England deep into Germany and back. 8, sometimes 10 hours in the air. During those 10 hours, the aircraft was not simply flying straight, It was constantly making small adjustments. Wind pushed it off course. Temperature changes at altitude affected engine performance. Ice could form on the wings, changing their shape and disrupting the airflow that kept the aircraft aloft. At 20,000 feet, the outside air temperature dropped to minus 22 degrees Fahrenheit, sometimes colder. The Merlin engines were designed to operate in these conditions, but maintaining that operation required constant monitoring by the flight engineer. Oil pressure, coolant temperature, supercharger settings. Each engine had its own personality, its own quirks, its own tendency to run slightly hot or slightly cold. The flight engineer sat beside the pilot watching gauges for 10 hours straight, adjusting throttles, managing fuel transfer between tanks, keeping 4 complex machines running in conditions they were pushed to their limits to tolerate. The Lancaster's bomb bay was the engineering feature that made it unique among World War II heavy bombers. Most bombers of the era had bomb bays divided into sections by structural frames running across the fuselage. These frames limited the size of individual bombs that could be carried. The Lancaster's designers removed those frames entirely, creating a single unobstructed bay running 33 feet along the fuselage centerline. This meant the Lancaster could carry bombs weighing up to 22,000 pounds. The Grand Slam earthquake bomb, a weapon so large no other aircraft of the era could lift it. Think about what that means aerodynamically. The Lancaster was designed to lift off with a bomb weighing 22,000 pounds suspended beneath its fuselage. At the moment of bomb release over the target, that weight disappeared in an instant. The aircraft suddenly became significantly lighter. Lift remained constant. The Lancaster lurched upward. Experienced crews anticipated this. Pilots held slight forward pressure on the controls at the moment of bomb release. Inexperienced crews who failed to anticipate it found themselves suddenly climbing through formations of other aircraft, dropping their bombs simultaneously. Getting to the target was only half the mission. The Lancaster also had to survive getting there. German anti-aircraft batteries tracked incoming aircraft using radar and directed concentrated fire at the altitudes where bombers flew. A shell burst near the aircraft could shred control surfaces, puncture fuel tanks, or damage engines without destroying the aircraft outright. This is where the Lancaster's 4-engine configuration proved decisive. 4 engines meant the aircraft could fly heavier bomb loads further and increased its chances of returning home if one or more engines failed or were hit by enemy anti-aircraft fire or fighters. A Lancaster that lost one engine lost roughly 25% of its thrust. It could still fly. It flew slower. It flew lower. It became more vulnerable to German fighters. But it flew. Aircraft that lost 2 engines on the same side faced a more serious problem. The asymmetric thrust tried to rotate the aircraft. Pilots countered this with rudder input, holding the aircraft straight against the force trying to turn it, for hours at a time if necessary, all the way back across Germany, across the North Sea, to a runway in England. Some made it. Some did not. The Lancaster's design gave them a chance that a twin-engine aircraft could not have offered. Landing a Lancaster at night after a 10-hour mission was a different kind of challenge entirely. The aircraft was now significantly lighter. Most of the fuel had been burned. The bombs were gone. That same wing that needed 105 miles per hour to generate enough lift for a fully loaded takeoff now generated more lift than necessary at the same speed. Pilots managed this with flaps. Extending the flaps changed the shape of the wing. The increased curvature raised the lift coefficient, the wing's efficiency at generating lift. This allowed the aircraft to fly safely at lower speeds during approach. Without flaps, landing at a speed that kept a fully loaded Lancaster flying would have required runways far longer than existed in wartime England. The approach was flown at roughly 93 miles per hour. Just before touchdown, the pilot raised the nose slightly, the flare, reducing vertical speed and letting the aircraft settle onto the runway rather than hitting it. After touchdown, the Lancaster's own weight did the work. The same 65,000 pounds that the Merlin engines had fought to lift off the ground now pressed down through the landing gear, creating the friction that brought the aircraft to a stop. The physics that made flight possible and the physics that ended it were the same physics. Only 2 airworthy Lancasters remain in the world today. 7,377 were built. Every one of those 7,377 aircraft flew on the same principles. 4 Merlin engines generating over 5,000 horsepower, a 102-foot wing generating lift through pressure difference and air deflection, a bomb bay carrying weights that should have been impossible to get airborne, 7 crew members managing the balance between all of these forces for 10 hours at a time over the most dangerous airspace on Earth. By common sense, something that heavy and that complicated should never have left the ground. But physics said otherwise, and 156,000 times, the Lancaster proved it. Now I'm curious, have you ever wondered how the Lancaster's engines kept running at minus 22 degrees Fahrenheit without freezing solid? That video is coming next.